All right, so the fundamental theorem of algebra says that your number of roots or number of zeros of a polynomial matches the degree. So on number 1, we are going to first start off by graphing this parabola. So it's x squared plus 4. So what is that plus 4 going to do? Like y equals x squared looks like this. We all know that. Kind of like that. What is the plus 4 going to do to that? It's going to shift it up. It's okay. So it's going to look like this. Maybe not as wobbly, but basically that's what it looks like. So if the fundamental theorem of algebra is true, and it is true, how many roots should this x squared plus 4 have? 2. All right, so up until today, the only type of roots you've learned about are real roots or real zeros. And what do real zeros look like on the graph? It's the x-intercepts, is where it touches the x-axis. So if we look at the graph, how many roots does it have? It has 0. So let's see what's happening to the 2 roots that it's missing. All right, if we want to find roots or zeros algebraically, you set the function equal to 0 and solve it for x. So what would you guys do first to solve that for x? Subtract 4. And then what would you do? Take the square root. And don't forget that every time that you're solving an equation by taking the square root, you have to take the positive and negative square root. So can you guys think of something that you can multiply by itself and get negative 4? Negative 2? Negative 2 times negative 2 is positive 4. Anything else? 4 times 4 is 16. You don't know one. There's not a real number that you can multiply by itself and ever get a negative. It doesn't happen. It just doesn't happen. So somebody a long time ago really didn't like it, that wasn't a solution. And I'm glad that they did, because this development of this imaginary number has helped people figure out things that happen inside black holes and all kinds of things with electricity. So there is a purpose to imaginary numbers. It's okay. It feels weird when you say that something isn't real, but there is a use for it. So anyway, this person a long time ago figured out that there is a whole new math world called the complex math world. And the square root of negative 1 is always equal to I, which is the imaginary unit. And so we can solve this equation. We can find the square root of negative 4 by rewriting the square root of negative 4 as the square root of negative 1 times the square root of 4. Because if I multiply those together, I would get the square root of negative 4. So we can do that. All right. And then what did we just say the square root of negative 1 is equal to? I. And then what is the square root of 4? 2, right? So this answer, there's 2 answers. 2i and negative 2i. 2 imaginary roots for that function, that when I plug them in, then I do get 0. Now, I don't want you to you can, but I don't really want you to go through this process where every time there's a negative, you make it the square root of negative 1 and then you make it I. What I really want you to be able to do, and it might take a little while since you haven't learned this before, is that whenever you see that there's a negative under the square root, that you just know there's going to be an I in your answer. So what do you guys think the square root of negative 25 is? It's just 5i. And what about the square root of negative 9? It's 3i. All right, so whenever you see there's a negative in a square root, there's going to be an I in the answer. And it takes like half a second. Half a second more difficult than what you've done before. Okay, And then yesterday we did factored form and zeros and all that. And we've done this before when you've had the zero and you've written the factor. So we're going to do that also for f of x. So there's two zeros, so we should have two factors. And when we've done these factors before, the first thing in the factor is always an x. All right, and then you just do the opposite of the zero. So if your zero is 2i, it should just be x minus 2i. If your zero is negative 2i, it should be x plus 2i is your factor. So your factors are going to look kind of weird today. They're going to even look weirder than that in a second. But it's the same idea. You do x, and then you do opposite. All right, I'm going to turn this fan back on. All right, so on number 2, we are going to find the zeros using the quadratic formula. So before today, we've been mainly factoring to find the zeros or factors or whatever. This one will not factor. I know that because there's only 2 things that multiply to give me 5, and they do not add to give me 2. So I know it won't factor. So do you guys remember this formula? Not at all? The quadratic formula? Some of you maybe. It's kind of hard to remember. There is a song. I'm not going to sing it, but I'll play somebody else singing it for you later if you want to learn it by a song. But what it does is it takes when we find the zero, we want to find when this is equal to 0. And so the quadratic formula takes the coefficients and the constant of this whenever it's in standard form, and in the end, it simplifies down to whatever the zeros are. So A is the coefficient of x squared, B is the coefficient of x, and C is the constant. All right, so x equals the opposite of b, so that's going to be negative 2, plus or minus the square root of b squared. So what's 2 squared? 4, minus 4a, 4 times a, which is 1, times c, which is 5, all divided by 2a, which is 1. All right, now we do not try to do all this in the calculator at one time. That's too much for your calculator. I mean, your calculator is really smart, but we're just going to do a little part at a time. All right, so we're just going to type in the calculator what's under the square root. We are not going to put the square root. So we're just going to do 4 minus 4 times 1 times 5. Or 4 minus 20, which you definitely could just do in your head. I don't know why. I felt like we needed to do it in the calculator. We could definitely just do it in our head. Sometimes the numbers are bigger and more difficult to just figure out in your head. So underneath that square root, we're going to have negative 16. Goodness, here we go. So what is the square root of negative 16? Yes, 4i. All right, and then our last step is to reduce. People mess this up like all the time, and they'll reduce early. If you reduce early, I promise it's going to mess you up every single time. So what I do is I wait to the very last step and I draw this heart. I'll draw it red, like a Valentine's heart. Oh, like a real heart. So that heart has to include every number in the problem that's not underneath a square root. And the only way you can reduce is if every one of these numbers reduces. Will every one of these reduce by the same thing, I should say? Yeah, they'll all reduce by 2. So then you just reduce everything by 2. And we don't really need to write a 1 in the denominator. All right, so this technically is 2 roots, or zeros. 1 plus 2i and negative 1 minus 2i. I didn't say it, but I should have said negative 1 plus 2i and negative 1 minus 2i. So that's very similar to quadratic formula stuff you did last year, except last year you never got imaginary solutions, you only got real solutions. All right, and then for part B, we want to write this in factored form. So this is where the factors are going to look kind of weird. So we have 2 zeros, so we are going to have 2 factors, but make them kind of wide. All right, so don't forget, with your factors, the first thing you put in the factor is x. And then after that is the opposites. So we're going to do opposite, opposite. And so instead of minus, we'll do a plus 1. And then instead of plus, we'll do minus 2i. Right? Now I know that's weird. You've probably never seen a factor like that before, but it's okay. Right? And then we'll do the same thing with the other one. So instead of this minus 1, we'll do plus 1. And instead of minus 2i, we'll do plus 2i. All right, and then for number 3, could a quadratic function have 1 real and 1 imaginary root? What do you guys think? It seems like maybe, but the thing is that, like, even with the quadratic formula, you have this plus or minus. If you were solving it like we did here, you have to do the square root, so there's always a plus or minus. So this actually is no. You must have positive and negative, and we'll talk about that more on the other side. So these imaginary zeros or roots are always going to be in pairs. You will never just have one. You will always have an even number of them. Okay, so on the other side, we're going to do a lot of the same things. So the fundamental theorem of algebra says, now this isn't like the actual theorem, but it's in real words, it says that the number of roots are zeros if you count the real, imaginary, and multiplicity. So for example, if you had something like this as a factor, you would count -3 2 times for the fundamental theorem of algebra. All right. Of a polynomial function is the same as the degree, or the largest exponent. Okay. And then today is the first time you're learning about the imaginary unit I. I is always equal to the square root of -1. So that means I is a letter, but it is not a variable. So you're used to letters being variables where, like, sometimes x is 2, sometimes x is -7. I isn't a variable. It is always the square root of -1. All right, then if I square both sides of this, I am going to get I squared. So what do you guys think I squared is equal to? If I square that square root, just -1. We may or may not use that very much, but it is something good to know. one thing we're going to use a lot today, and when you do your assignment tomorrow, is that imaginary roots come in conjugate pairs. Right, so a conjugate pair, so this is, we'll say this is a generic imaginary number. A is what's called the real part, and BI is called the imaginary part. And so the conjugate is going to have the same real part, but it's going to have opposite imaginary parts. So if A plus BI is a root, then A minus BI is a root. All right, so I'm going to skip this one for a second and go to 2 minus 5i. All right, so if 2 minus 5i is a root, then we would do the same real part. And then we're going to do opposite imaginary parts. So 2 plus 5i is also a root. Yes, ma'am? What if you don't have a real part? So what do you think is the conjugate for 3i? What do y'all think? Yeah, it'd just be negative 3i. Good. And we saw that, like on the front side we had 2i and negative 2i. They're always going to come in pairs. All right, one other note is that irrational roots also come in pairs. So an irrational, and there was a joke about on the front that I just kind of ignored that. I is telling pi to be rational and pi is telling I to get real. But anyway, pi is an irrational number, but anytime you have this square root of a number that's not a perfect square, it is also an irrational number. And so they come in pairs also. So if a plus the square root of b is a root, so is a minus the square root of b. Right? If negative 6 is a root, negative square root of 6 is a root, so is positive square root of 6. And then negative 5 plus the square root of 2 and negative 5 minus the square root of 2. They're all always going to come in pairs like that.
I got a question.
Yes?
How come like the negative 5 and stuff doesn't change on
The real part, it won't change. Because that's kind of like what's in front. Like if we were doing the quadratic formula, that's this thing here. And so it's going to not change sign. But what's after the plus or minus is what changes sign. All right. That was a good question. What other questions do you guys have? Okay, so let's do some of these. On number 1, we are going to find all the roots. So factoring is always the fastest way to do it if it will factor, but it only takes a few seconds to realize it won't. So if this was going to factor, you would need to multiply to get 4 and add to get negative 1. Is there any way that can happen with stuff that multiplies to get 4? 2 and 2 and 4 and 1? No. So we're going to do the quadratic formula, so let's jot it down. X equals the opposite of b plus or minus the square root of b squared minus 4ac divided by 2a. All right, and we want x squared minus x plus 4 to equal 0. So you guys jot down what a, b, and c are, please. And then we're going to take that a, b, and c, and we're going to plug them into the quadratic formula. So we're going to do the opposite of negative 1, which will be positive 1. plus or minus the square root of negative 1 squared. So what's negative 1 times negative 1? 1. Minus 4 times 1 times 4 divided by 2 times 1. All right, and then you can either do this in your head or in your calculator. It doesn't matter. I think we can do it in our head faster, actually. So 4 times 4 is 16. So what's 1 minus 16? Negative 15. All right, and then this is the first one we're doing where that isn't like a negative version of a perfect square. It's actually easier. So in this case it is. It's not always. So I know because there's a negative under the square root that I'm going to have it I, and then it's going to be a positive under the square root. So you pull out the I and it becomes a positive. That sounds kind of gross. And then as long as there's not a perfect square that divides evenly into 15, then we're done. So the only perfect squares that are smaller than 15 are 4 and 9, and 1 doesn't count. Will either one of these divide evenly into 15? No. So that's it. All right. So number 2 wants us to use technology to determine the number of real and the number of imaginary zeros. All right, how many total zeros should this function have? It's whatever the degree is. So it should just be 6. So whenever it's in standard form where there's no parentheses, is the easiest way to do the degrees. Just look at the largest power. All right, so that's counting all imaginary, real, and multiplicities. There should be 6 total zeros. All right, I think I still have this typed in from last period. I do. So let's just look at the graph. Did anything weird happen at these, like a bend or a bounce, that would say there's a multiplicity? Or did I just go straight through? I just go straight through, right? You would be able to tell. It would have like a weird squiggle. Yeah, these just go straight through. So that's 2 real zeros. But this is supposed to have 6. So what about the other 4? They're imaginary. Imaginary zeros never show up on the graph. So the real zeros are the x-intercepts, and then however many are left to get to your total, that's going to be the imaginary. Okay. And then for number 3, I kind of like questions like this. So we know that 6 plus I and 4 minus the square root of 3 are roots of a 4th degree polynomial function. We're going to find the remaining roots, and we're going to write the function in factored form. So how many total roots should there be? 4. All right. So we have 2. And we can use those 2 to find the other 2. So we're going back to this whole idea of conjugate. So all this stuff we did right here and right here, that's what we're going to do. That's what we're going to use now. Okay, so if 6 plus I is a root, what else is a root? You knew this a second ago.
6.
Thank you. 6 minus I. So same real part, opposite imaginary part. All right, and then if 4 minus the square root of 3 is a root, what else is? Thank you. All right, so those are the remaining roots. So now that we have all 4, we can write this function in factored form. So 4 roots means we're going to have 4 factors, so make them kind of wide. And the first thing in each factor is just going to be x. All right, and then we'll go back and just do opposite, opposite. So I'll just start with the one with the 6. So 6 plus I means that it's going to be minus 6 minus I. Right? And then I also have 6 minus I. So that one is going to be minus 6 plus I. All right. So you guys do the 2 factors with the 4 and the square root of 3, please. All right, any questions? Okay, and then the last question is something that you might have seen on the ACT. So I was really pretty frustrated that they took imaginary numbers out of Algebra 2 because some of you seniors might not take the ACT again, and there definitely is a question or two that uses this imaginary unit I. If it was one like this, I think you might have been able to figure it out without knowing what I is. They do tell you. But you don't really need to know that to get this answer. So what do you think you do to add these 2 numbers together? Okay, you just add the like terms basically. You would just add 7 and negative 8. And then you would add 3i and 9i. And not knowing what I is, I think you might have figured that out on your own. Just think of it like an x, even though it's not. All right, what questions do you guys have?